In previous lectures, we installed Truffle and Ganache that can easily emulate an Ethereum node for development purposes. While these fake Ethereum nodes are an easy way to test your application, you have to keep in mind that they are just emulators. They provide the same interface as an Ethereum node deployed in the public Ethereum network, but internally they work completely differently. If you want to ensure that your contract will run properly on the main network, it is highly recommended to test it with a full Ethereum node. In this lecture, we will install a private Ethereum instance with Geth on Windows. If you are on macOS or Linux, please jump to one of the other lectures that describes the installation process for your operating system. Now let's start a new PowerShell window to create the folder that will host the database and all the files for our private node. Again, I should do everything in PowerShell on Windows. That will be easier. And the first thing I need to do is to create the chainskills/private directory under my user home directory. And to do that, I can just run mkdir. That's the PowerShell command to create a directory. -p to create all the parent directories on the path of the directory I want to create. And then I can specify chainskills/private since I am in my user directory already. So now if I go to the chainskills subdirectory in my user directory, I will find the private directory under there. Now before creating our private instance, we have to define the genesis block. That is the block that will define the initial behavior of our blockchain instance. Creating a genesis block from scratch can be painful, and reusing an existing one can be a problem if its version is older than your current installation of Geth. To ensure that your genesis block file is compliant with your version of Geth, we will create it using a tool called Puppet. Puppet is a command line tool that is installed with Geth and that provides features to create and monitor your own Ethereum network. So here we will use Puppet to create the genesis block file. First, make sure that you are in this chainskills/private directory under your user home directory, and then you run Puppet, like that. Again, this was installed when we installed Geth. So the first thing we have to do is to choose a name for our network, and in our case we'll just call it chainskills. And then we have a menu with several options. In our case, we'll use command 2 to configure a new genesis. Which consensus engine to use? We have a choice between Ethash, which is a proof of work, or Click, which is a proof of authority. We want it to look like the real thing, so we'll use the first option, the Ethash. Which account should be pre-funded? We'll just leave it like that and type enter. Then we have to choose a chain or network identifier for our network. Important thing is that this ID must be different from the IDs that are already used for public networks. So the ID 1 is reserved for the mainnet. ID 2 is reserved for the modern test network, which is now obsolete. Number 3 is for the Robston test network. Number 4 is for Rinkeby, another public test network that we will use later. And 42 is for Kovan, another test network. In our course, we will use the network ID 4224. So you can type 4224 and enter. Anything fun to embed in the genesis block? No thanks. And that's it. So now we created the genesis, but we still need to export it. So it created it in memory if you want, and we want to export it into a JSON file. To do that, we choose option 2, manage existing genesis, and then option 2 again for exporting genesis configuration. Here we can choose a name for the file. We'll just keep the default, which is chainskills.json. And as you can see, we have this that says exported existing genesis block. And now our work with Puppet is done. So we can quit by just typing Control-C on our keyboard, and that's it. And we go back to the prompt. By the way, if you type ls to list the content of the directory, you can see that now we have this chainskills.json file, and we can open it with Atom by just running it like that, Atom chain_skills.json. So here's the content of the chain_skills.json file that we will use to initialize the private node. And here are the most interesting items in this Genesis file. The config is a section that is used to define the parameters for the chain. The network identifier is defined in the chain ID field. And config also contains the block numbers from which to apply various hard fork rules that have been added to Ethereum chain over time. For example, the Byzantium hard fork will be applied from block number 4 in this private network. Then we have the timestamp field, and this is used by the Ethereum virtual machine to adjust the level of difficulty that must be applied. If the timestamp difference between two blocks is too small, the difficulty will be increased. If the timestamp difference between two consecutive blocks is too high, the difficulty will be reduced. And the timestamp is also used to ensure that blocks are in the correct order. After that, we have the extra data field where we could have set some custom data. We didn't do anything here. Gas limits define the maximum value of total gas that transactions in a block can spend. So this value is here to limit the processing requirements of each block and in effect limit the size of blocks. In a private node, you can set this value to the maximum while keeping in mind that you have to measure the gas spent by your transactions. The difficulty fields defines the difficulty level that will be used to validate a block, which directly correlates to the average number of times a miner will have to run the hashing function to solve a consensus puzzle. On a private blockchain instance, it is recommended to set a lower value to reduce computation time. Then Coinbase is the address of the account that will get the mining rewards for this block. So in this case, we don't know yet, so it's 0, but when this block is mined, it will get the address of the miner. Then alloc is a section where we can pre-allocate funds to some wallet addresses. And this block is pretty big, but we can reduce it here in Atom. Then we have number, that is the block number, and since it's a Genesis block, it's block number 0. Gas used is the sum of all the gas used by all the transactions in this block. There is none, so it's 0. And finally, parent hash contains the hash of the parent block. And again, since we are in the Genesis block, it has no parent, so that's the only block where the parent hash is 0. So let's leave Atom. So now that we have our Genesis file, let's use it to initialize our private node. The private node will be created using the get command with the following parameters. Datadir will be used to set the target directory where the private node data will be saved. Knowing that without this parameter, the node would use the folder for the main public net, and of course that's not what we want. And we'll also use the init command to specify the Genesis block to initialize the private node. Okay, so from within this private directory under chain skills under the user home directory, we can use the following command, get --datadir. So we'll save all the data in the local directory, in the current directory, and init chain_skills.json. So we're using the chain_skills.json as a Genesis block to initialize our node. We can run this command, and we can see that the data for the node will be stored under geth/chain data inside the private directory. So now we have, in addition to our chain_skills.json Genesis file, we also have a geth directory and a keystore directory. Geth will store all the data for the chain, and keystore will store all our accounts. And by the way, if you go to keystore and you list the content, there's nothing. Let's come back up. So now we will create 3 accounts that we will use in this course. The first one will receive all the mining rewards, and the other 2 accounts will act as the buyer and or the seller of the articles in the chainlist dApp that we'll build later. To create those accounts, we will use the geth command and specify the path of our private node and the account new command. So here, geth --datadir dot That means the current directory. And we use the account new geth subcommand to create a new account. Your new account is locked with a password, so each account will have a private key, and this private key will be protected with a password so that it can only be used to sign a transaction with the password. So here for all the accounts, we are going to use pass1234 by default. If you change that password, don't forget to adapt it later on. Pass1234, we type it a second time, and we get a new account, and that's the address of this new account that we just created. And we can run this command 2 more times. You can use the arrows to recall past commands. So we run this command again to create a second account. Each time it's a random one. Pass1234. And there is our second account. And we do it a third time. And that's it. We have our 3 accounts. Of course, these addresses will be different for you as they are randomly generated. And now, if you go to ls key store, for example, if you type ls ./keystore, you will see that our key store directory now contains 3 files, one for each account that we just created. To list the account and get their position in the list, we can use the account list command, a subcommand. So geth --datadir always dot and then account list, and then we get a list of accounts with their respective index, their address, and the file where they are stored. By the way, by default, the first account, so the one with index 0, that one, is the one that will receive all the mining rewards when we start mining. So far we initialized our private node and we created 3 accounts for it, but it hasn't started yet. In order to start our private node and start mining blocks, we'll create a script that will define all the required parameters to let us interact with our private node. Note that this script, that will be called startnode.cmd, is attached as a resource to this lesson, so you can download it and use it as it is. I'll just go over the content of this file to explain all the command line parameters. So here we'll create the file with Atom by using Atom and then typing startnode.cmd. That's a command script. And it will open Atom with this file, this empty file open for us to edit. Let's maximize this. Close the chainskills.json file, we don't need that anymore. And let's start typing the command. So of course it's geth to start geth, and then network ID to specify the network identifier. --mine will start this node, we'll start the miner on this node right away. And we can also specify the number of threads on which we want to mine. And in that case, I'm going to use miner threads 2 because I know that I have 2 cores on this machine that I can use for mining, but you can choose 1 or, however you want to configure it. But keep it low, otherwise it will eat up all your processing power on your machine. Then we can specify the datadir command line argument to indicate where we want to store our chain file. And here we'll just put in the current directory since we'll only run this start node command script from within the private directory. Then this node will be an isolated node, so we don't want it to be connected with other nodes, so we'll deactivate the discovery protocol, so --no discover. What we want though is to enable the RPC endpoint because we'll use that to connect to our node using MetaMask later on, so --RPC. And we can also specify which port we want this node to listen to, so --RPC port within double quotes 8545. Then we can also specify the discovery port, even though we are not using the discovery protocol. and that by default is 30303. Then we want any domain to be able to connect to our RPC endpoint. So --RPC course domain, that would be a star. There's this argument that's used for networking, --NAT, the value will be any. And then we also want to activate a certain number of RPC modules, and those are modules for commands that we will be able to use in the RPC endpoint. So here, --RPC API, and then we can list the modules that separated by commas. So there will be ETH, Web3, personal, and net. Net. Then we want our node to mine, so we have to unlock the account that will be used to receive the mining rewards. And that case will be the account number 0, so --unlock, after which we have to specify the index of the account to unlock, 0, --password, because of course if we want to unlock this account, we also need to specify a file that will contain the password. So here we will create this file under password.sec. And we'll create this file in a second. So again, the content of this script is very critical. So we really advise you to download the script as it is from the resources of this lecture. And also make sure that the whole content of this file fits on one line. If you put it on several lines, if you add any line feed or carriage return to this file, then everything that's not on the first line will be ignored. And then you will have issues connecting to the node and so on. So make sure that it all fits on one line. So here we save the file. And of course, before we can run the script, we have to create the password.sec file that will store the password of the first account. So from within Atom, I can right-click the private directory here, click New File, and then type password.sec as a name for the file. And in there, I just type pass1234, which is the password for the first account. And I don't forget to save that file as well. Now we can run our node. So first, let's leave Atom, go back to the PowerShell, clear the screen a little bit, and then from within that directory, that private directory where we just created our password.sec and startnode.cmd, we can run startnode.cmd with /startnode.cmd, and then it will start the node. I will shut it down right away with Control-C, just to show you the beginning of the file. Confirm, okay. And then if we scroll back up to the beginning, there are a few very important elements of information that we can find. Well, first of all, we can see the entire command that is run when we run the script. And that is very important to see that all the command line parameters that we specified in the file were taken into account. Then we can see starting peer-to-peer node on instance with Geth 173. That's the version of Geth that we are using, so that's okay. We can also see that the chain data is correctly stored under the Geth directory, under the private directory, in chain skills, in our user home directory. That was the intended place. We can also see the configuration that we specified in the Genesis file with the chain ID, with the homestead block, with the EIP blocks and so on, the Byzantium block on number 4 and so on. All the things with the fhash DAGs, we'll talk about it later. And another thing that's important is that we can see here HTTP open, endpoint open on port 8545. So that's good, that's what we wanted. And another thing that's important is this IPC endpoint opened on this obscure file path. This is important because this is the default endpoint, and get attach later will look for this IPv file to connect to our node. But on Windows, we cannot customize it anyway, like on other systems, so that's okay. Then we have confirmation that this account is unlocked, and that corresponds to the Coinbase account as we created it before for this node. And we can see that right before we shut it down, it was starting to commit new mining work. Okay, now let's start it again. And you will see that after this metadata information about the running of the node, we can see that it's starting to commit mining work. Before it actually starts mining, it needs to generate a DAG. Now the DAG, or Directed Acyclic Graph, is a data structure that is needed by the Ethash mining algorithm to do its work. It is generated every 30,000 blocks, which is called an epoch, and it is stored in a file under appdata/ethash. And that is what we can see at the beginning of the logs here. Yeah, disk storage for ethash DAGs. You can see it's under appdata/ethash. So generating this DAG will take some time, the first time, and it may even take a few hours on some machines. So if your laptop is old, it doesn't have a lot of memory and so on, this might take a while. But the good thing is that you can follow the process, the progress of this procedure by looking at the percentage field in these lines. And basically it will do it for epoch 0. And once it reaches 100% for epoch 0, it will start doing it right away for epoch 1, and it will reach 100% again. But as soon as it can, it will start mining. So this will take some time the first time, but then it should be straightforward. One important note that you might be concerned about: why will our node mine, and why did we already start committing new mining work when we didn't send any transactions yet? Well, first of all, it has to mine the Genesis block. That was the first one. But then you will see that the node will start mining blocks on a regular basis, even though it doesn't get any transactions yet. This is normal because you have to keep in mind that the mining process, its role is not just to mine transactions into blocks, it's also to create new Ether, new currency. And this new currency should be created on a regular schedule. So every few seconds, for example, a new block should be created, should be mined to create a new quantity of Ether, whether there are pending transactions or not. So for usual implementations of this proof of work algorithm on Ethereum, even on the mainnet, you can find blocks that are actually empty and don't contain any transaction. Now, if Geth seems to be stuck for several hours on one of these steps, so on the DAG generation process in particular, it might mean that you forgot to initialize your node with the Genesis file, or you forgot to create some accounts, or there is a mistake in your startnode.cmd, or your chain data is corrupted for some reason. So your best option in these cases is just to delete the private directory altogether and to do the whole procedure again. Don't forget that you can download the startnode.cmd script from the resources attached to this lecture to be sure there is no mistake in it. And if after all that your private node doesn't start mining as it should, feel free to copy-paste as much of your startnode.cmd console output, what we are seeing now, into a question in the Q&A section of this course, along with the content of your startnode.cmd script. And we will help you troubleshoot what is going on. So now we will just leave it running and let it go until the end of the DAG generation process, and we'll come back when it's done. So as you can see, once it's reached 100% for epoch 0, it will start mining and calculating the dash for epoch 1 as well. And again, an epoch is a period of 30,000 blocks. So here it has already started mining new blocks, but the DAG generation process is going to take most of the processing power of the machine, and we have to wait for epoch 1 to be calculated before we can connect to our node from the outside. So here we reach the end of the DAG generation process for epoch 1, reach 100%. And now all our node is doing in the background is just mining new blocks. And while it was calculating the DAG for epoch 1, it already mined 20 blocks or so. Yeah. And now it's mining new ones on a regular basis. So now that our node is mining, we can attach a JavaScript console to it. So we'll leave it running here and we'll open a new PowerShell window by right-clicking on the PowerShell button in the taskbar and then clicking on Windows PowerShell again. And this will open a second PowerShell window and leave the other one running. So here, now that our node is running in the background, we can run get attach. And this will open a JavaScript console that is attached to our running node. And here we have a few pieces of information that we can use to confirm that we are connected to the right node. So the data dir is in chain_scale/private, so that's okay. We have a certain number of modules that are available over the IPC endpoint, and the code base seems to match the one that is used to mine. In general, when you want to get attach a console to a running node, make sure that you don't have plenty of nodes running in the background, like a mainnet node using Mist or whatever. Here we only have our private node running, and we are connected to it with the get attach console. Ganache that we will run later is running on a different RPC endpoint, a different RPC port, so that should be okay to run in parallel. But the private node, we shouldn't have many other nodes running beside the private node. Now, when you run get attach, if you get a message like fatal unable to attach to remote get, timed out waiting for pipe, and with more details after that, it means the private node is not properly started. So again, check the content of your startnode.cmd, or even better, download it from the resources of this lecture and use it as it is. Now, within this JavaScript console, we can type commands that are exposed through one of the APIs, and we will show you a list of those commands now. So the first command that we can use is eth.accounts, and this will list all the accounts that have been registered on this node. And the first one is eth.coinbase, and this is the address. We can also query the balance of each account by using eth.getBalance and specify the account for which we want the balance as a parameter. So for example, if we want the balance of the Coinbase account, we can type this command. And here we can see that we already have some Ether on it. And if we do the same thing for account 1, for example, eth.accounts1, here we have 0. Now, what's important to understand is that this getBalance function returns the balance in Wei. So that is 10 to the minus 18 Ether. That's the most elemental unit of value. And if we want to convert it to Ether, we can use web3.fromWei as a function and pass it eth.getBalance for eth.coinbase and specify the unit in which we want to convert. So here we see that we have 147 Ether on this Coinbase account now. You can also use miner.stop to stop the mining process. And now if we go back to the other console, we can see that the mining process stopped. And we can start it again. And we can even specify the number of threads that should be used to mine. So here I'm mining on one thread again. updated mining threads equals 1, started mining operation, and now it is going to mine slightly slower because it's only using one thread. By the way, you can find a comprehensive list of commands on this link, and that link will also be in the resources of this course. I'm just going to show you a couple more. So let's go back to the console. You can also use net.version to get the network identifier. And you can use functions from the personal module to unlock accounts. Now, unlocking an account means basically opening the private key for access to signed transactions. By default, private keys are locked and they can only be used if you know the password. And you can unlock them for a certain duration so that they can be used to sign transactions. By the way, when we start the node, we unlock the account with index 0 to receive mining node and be able to write blocks in the chain. Now let's say we want to unlock accounts with index 1. We can type personal.unlock account, eth.accounts 1. Then we need to specify the password and the duration for which we want to open it. So for example, 300 seconds, that will be 5 minutes. And if we get true, that means the account has been unlocked. We can also do it more simply by typing personal.unlock account, and this time we'll unlock accounts with index 2 accounts without any other parameter. And there it will ask for the passphrase for this account. So pass 1, 2, 3, 4. And the default duration, I think, is 10 minutes. Now, before closing this lecture, we will transfer some Ether from the Coinbase account, the one that is linked to the mining process, to the 2 other accounts. To transfer 10 Ether from the Coinbase account to the other 2 accounts, we will use the eth.send transaction function. So eth.send transaction, and that function takes only one parameter in the form of a JavaScript object. And this JavaScript object will have 3 fields. The first one is the from, which is the address from which to send the funds. So eth.coinbase in our case. Then we have a to field that will contain the address of the destination accounts. Okay, and then we have the value field that will contain the number of ways that we want to send from account 0 to account 1. And to do that, instead of doing some complex calculation, we can also use the web3.toWay function. So earlier we used the fromWay function. Here we can use the toWay one. And we want to transfer 10 Ether from one account to the other. And when we send that command, what we get here is the transaction hash. So a new transaction was created and sent to the node. And if we go back to the other window, we can see that a transaction was submitted. And as a result, it was included in one of these next blocks. We'll run this command again to send 10 ethers to account with index 2. So we can just call back previous commands with the arrow keys. So arrow up will call back the last command. And this time we want to send from Coinbase to account with index 2, the same amount, and another transaction is created and will be mined. And here's the other transactions. So now we're assuming that both of those transactions have been mined into blocks. So we should be able to get updated balances. So again, we can call back previous commands. So for example, accounts 1 now has 10 ether, and account 2 has 0 ether as of now. So that means the second transaction has not been mined yet. Let's do it again. Okay, there's something wrong here. Let's wait a little more. And there we go. Now account 2 has the 10 ether. So again, keep in mind that if the mining process is stopped when you send transactions to it, they will not be mined into new blocks, so they won't have any effect on the chain itself. The last thing we need to do is to exit this Geth console, and to do that we can just type exit and enter. And then to stop, so we can close this PowerShell window, and then to stop the running node, you can simply type Ctrl-C on your keyboard, confirm if you want to terminate the batch job, and you can just type enter or Ctrl-C again. So in this lecture, we explained how to create a Genesis block file with Puppet. We initialized a private node with a Genesis block. We created 3 accounts. We started the private node. We attached a Geth console. We checked the list of accounts and their balances. We started and stopped the mining process, and we sent some Ether from the Coinbase account to the other 2 accounts. Again, don't forget that you can find the Genesis file and the startnode.cmd script attached as resources to this lesson. In the next lecture, we'll show you how to install MetaMask in the Chrome browser.